Okay, so welcome everyone to the afternoon and a session for Paris, a morning session for New York. We'll have a 1 hour flash talk session, and the first one is Adam Andrews, and Adam will speak about field level inference of primordial non-Gaussianity using next generation surveys. Each speaker, you have 3 minutes. Please keep your time, otherwise you will hear me. Thanks.
Sorry, I have 12 minutes, no? Or is...
Sorry. Yes, the first one is 12, yeah.
Okay,
and after that, everybody is 3 minutes.
Good, good, just we're on the same page. Okay, good afternoon, everyone, and good morning to New York. I'd like to start off by thanking the organizers for this wonderful event. It's been very inspiring so far. So my name is Adam Andrews, and I'm a postdoc at Bologna. And I'm here to talk about a little bit about what I'm doing in terms of doing method preparation for the Euclid satellites data, but also the work that I've been doing during my PhD at Stockholm University. And that has to do with field level inference of primordial non-Gaussianity, kind of constraining cosmological parameters using a field level inference approach. Kind of start off with putting the work in context. I'd start off with this kind of typical cosmological slide where we have, which depicts the history of, of our universe, basically, with the x-axis representing time and the y-axis representing the expansion time of the universe, or the expansion of space-time of the universe. So on the left-hand side, we have the observables, what we can observe today with the large-scale structure and typically galaxies. On the left-hand side, we have kind of the beginning, the origins of the universe. And in my talk, I'm kind of fixated on inflationary theory and how to probe cosmological inflationary theory. And basically, that has to do with where all of the primordial seeds came from. So I'd like to break down cosmological theory into the question of how many fields were actually active during cosmic inflation. So were there one field and we kind of get nice Gaussian-like statistics, initial conditions, or were there several fields kind of perturbing this initial field, basically? And the way we parameterize this non-Gaussianity is with the FNL parameter, the local form of the primordial non-Gaussianity parameter, which is a scalar and constant over space and time, basically. And this is then to the first order first order perturbation to the squeezed shape, as it's called. And really, the key value that we're looking for is to kind of differentiate between zero values, or close to zero values of FNL, as dictated by the Maldacena relation, and non-zero values, or values far from this Maldacena consistency relationship, and to be able to make this statement. So basically, if we would be able to detect a significant non-zero value of FNL, this would indicate that there were more fields responsible or active during the phase of cosmic inflation. To kind of swing over to the observational status, I kind of summarize the current result in this plot here. So we have the results from the cosmic microwave background in the center with the gray posterior, which has nicely constrained FNL down to the order of ±5. However, the issue is we've already kind of probed the largest scales with the cosmic microwave background through Planck. This is kind of where we get the most information to constrain primordial non-Gaussianity. So instead, we're turning our attention in order to meet this goal in the middle, which is kind of set by the next generation of galaxy surveys with this yellow bar in the middle. We kind of want to reach the level of ±1 in order to make this definitive statement, or this statement on the number of fields during cosmic inflation. So these blue and these grid posteriors here kind of represent the current constraints that we can get through galaxy surveys, through SDSS-3 and with quasar extensions of the EBOS survey, where we can reach the order of ±20, ±15-ish. So we're kind of still far out yet with these data sets, and hence we need the next generation of galaxy surveys. However, note one thing, that we're basing these measurements on bispectrum and power spectrum estimates. Basically, we're using summary statistics to kind of constrain primordial non-Gaussianity. And what I would like to, the question that I'm also trying to answer in this talk is kind of the question that Adrian Bayer mentioned yesterday, is basically, can we do better? Can we go beyond using summary statistics? Can we use the full field instead of relying on summary statistics to constrain FNL? And to kind of put this more into context of primordial non-Gaussianity, why we believe that we would be able to make, or to be able to get stronger stronger constraints from the full field. I like to show off this slideshow animation, basically. On the left-hand side, we have the initial conditions, this Gaussian field. In the middle, we have the resulting final density matter field in the present-day universe. And on the right-hand side, we have the corresponding galaxy field, kind of evolved through a galaxy bias model from the final density matter field. So these three slices, we can kind of see how they evolve as we crank up FNL into very large values. Note that these are, of course, quite far off from the current constraints, but they're kind of to show illustratively how the fields are affected, how the cosmic fields are affected. We can kind of see on the left-hand side, of course, as we expect, the Gaussian field turns into a non-Gaussian field. The final density field has this effect, which is depicted or mentioned in the seminal paper by Dalal et al., where we kind of have these more fully evolved filaments, and where we have more growth, basically becomes even more enlarged. And these underdense regions become even more smoothed out, basically. On the right-hand side, we see the galaxies prefer these overdense regions much more than they prefer the underdense regions, which is known as the scale-dependent bias effect. And basically, what I want to do or demonstrate in this talk is that I want to go beyond all of these summary statistics that rely on a limited amount of probes in the cosmic field, and instead I want to use the full field to fit the full field directly and constrain FNL from using all of the information that is available in the cosmic field. And I do this through using a field level inference approach. So I kind of usually explain field level inference as a combination of two components. So first, we have a forward model. With a forward model, we can transform any set of initial conditions discretized on a 3D cube. We can forward evolve this using a primordial power spectrum, perturbing with FNL, evolving thereon with a structure formation model, and using physical models to kind of see how the field is transformed under redshift distortion effects or light cone effects, and applying a galaxy bias model and any type of survey selection effects to constrain or to make a prediction on the final observable. And this we can then collapse to a likelihood, so we can then place it into a Bayesian framework where we compute an explicit likelihood. Now, this data model is also differentiable, meaning that we use a Hamiltonian Markov chains to kind of guide the sampling procedure, and thus we can achieve this non-compressed exploration of the posterior. So we can kind of place this into a statistical inference framework and sample from the posterior. Similarly to how we would sample from a 2D posterior, we instead have a posterior under order of 10 to 100 of millions of parameters, each corresponding to the density fluctuations in the field, basically. So I mentioned some of the highlights of field level inference, and the main thing for primordial non-Gaussianity is that we'll be able to combine all of the probes jointly together in a consistent framework to constrain FNL, basically. Now, before I go on and mention some of the results that we've gone so far, I'd just like to highlight when I'm at this stage that later on today, Ludwig will be talking about how we can use field-level emulators to kind of speed up the structure formation model. We've been relying on LPT and 2LPT to kind of simulate this, but Ludwig has been working on a project to kind of speed these results up. Simon will be talking tomorrow on how we can use machine learning models to kind of guide the modeling behavior of basically how to transform from the density field to a final galaxy observable and halo mass functions and so on and so forth, something that we can measure, basically. Jens will be talking tomorrow about Borg and giving a broader overview of Borg and other applications of Borg. And I also like to mention Vincent will be talking later today. So Vincent will be talking about how we can use another interpretable machine learning approach to kind of use Hamiltonian dynamics to guide normalizing flows fitting, basically. Okay, so kind of the first paper that we had out on this has to do with the proof of concept. So basically what we do is that we take a survey, an SDSS3 survey, extract key features from this, the radial selection function, sky completeness maps, and we inject a non-zero value of FNL to kind of see if we can retrieve this value from the generated mock data. So we kind of have a fiducial mock data set that we analyze using, that we generate with the same forward model, but we also then analyze. We're using a self-consistent mock data setup. And the results have been quite promising so far. We be able to infer and recapture as well the fiducial FNL value, making a forecast on tight constraints on the values. And this then we can make the statement on this full posterior that it is actually capturing the full information content available in the data to jointly use this to constrain primordial non-Gaussianity. And just to compare with a current real data analysis for primordial non-Gaussian using SDSS3, we see that our results are quite promising in that context. So in the interest of time, I'd actually like to skip this slide. Sorry for this. So this discussion a bit more of the results. And I'd like to go on to this last point that I have here, robustness to systematic effects. Now, one opportunity or one advantage, basically, of field-level inference is that we have a data model which is physics-informed, basically. And what this means is that Borg, this algorithm that we place the field-level inference algorithm in, is able to distinguish between physical effects and non-physical effects. And basically what we can do is that we can marginalize these out or integrate out these unphysical signals. Moreover, we can perform posterior tests of these large-scale systematic contaminations and kind of see what Borg picked up that was kind of what it didn't expect, basically. And this has been published in a work by Guillaume Lavaux, where we can have these foreground contaminations in the SDSS3 catalogs. Florent will later today also talk a bit more about this approach, but also extend it and show how we can extend it to likelihood-free inference as well. And this kind of round off the talk with kind of keeping this the systematic free approach in mind. We've been kind of working on doing a qualia analysis, Arthur Loureiro and I, who's a postdoc at Stockholm University, where we have the qualia data set, which came out this summer, a very nice quasar compilation from the Gaia data set made by Kate Story-Fisher, among others. And basically, what's nice about this data set is it's fairly full sky, about 0.7, very large volume as well, about 10 gigaparsec in total box size, basically, from end to end. There are some challenges, though. It's kind of sparse. It's kind of shot noise dominated in that sense. We have this very large volume, but we only have 1.3 million quasars tracing the cosmic field. And we also have to have control over the spectrophotometric uncertainties that are related to this. So what Arthur and I kind of set out to do is to make a large-scale reconstruction of the density field using this quasar data set to kind of see if we can infer any systematic contaminations that are in regards to this data set, and also, yeah, to see if we can combine this with other data sets, and also to see if we can combine this doing cross-correlation analyses. So with this final image, I'd just like to highlight that the data set is quite well documented. There's a lot of content available, so we really appreciate that. Arthur and I just like to mention that it's a very nicely written paper and documented repo. So rounding off with some so far inferred density fields. So these are slices over the central of the data of the density field that we've kind of inferred so far at a kind of a low resolution. And also that we can kind of see that our power spectra over the entire analysis chain have kind of converged and are seem to be sampling from a posterior. But more checks, more results are kind of needed, and we're kind of digging into the data more and more. So yeah, to kind of run off for primordial non-Gaussianity, promising results. We can have this kind of novel approach to include systematic effects into the analysis, and we can also produce additional data products such as inferred density fields. Thank you very much.
Thanks, Adam. Is there any question in the audience? Yes, there.
Thank you. Nice talk. I was curious, were you also varying the other cosmological parameters when inferring the non-Gaussianity, or were you fixing them?
No, we're fixing them to Planck values, Planck best fit values. So that for the mock data, we kind of fix it, and then we inject it with their own. But of course, that can maybe be an issue later on when we do with the quia.
Do you expect a big change if we were going to vary the other Cosmo parameters?
With FNL?
Apart from FNL, if we vary all the Cosmo parameters.
Well, there are some other studies as well within the Borg framework or within the Aquila consortium where they're kind of working on doing other cosmological parameters. I'm just not too focused on that. In regards to my results, I mean, I would expect some sort of degeneracy, of course, but I'm not sure entirely how
Thank you.
That is.
I see no question on Zoom. Any question from New York?
Any questions? That's fine.
No.
Hi, great talk. I was just wondering if with the mock data set that you made with FNL equal to 5, did you use a standard non-field level inference approach to try and infer that parameter, and what kind of constraints you get?
Unfortunately, no, I have. Sorry. Okay, I think I heard the last end of that question as well. No, I haven't really done, I have not, with the same mock data, done using other estimators. That's kind of what I've been looking into as well, but I haven't really developed such an estimator. I got into that point yet to produce any constraints. But that would be, yeah, I agree. That would be interesting to kind of make a fairer comparison. Definitely.
Thank you.
Okay, let's thank again Adam.
Thank you.